I'll be here for flex tomorrow. Whoa, what happened? So hopefully you watched the videos for 4.1A through E, but we are going to go through some of the concepts today, as well as moving on to 4.1F. Because, you know, everybody finishes the test at different times, and if you finish early, you will be able to do a little bit of the 4.1F worksheet, and then after that, we're going to learn the rest so you can do the rest. Hello? Oh, okay. So, tell me, what is a Bronsted-Lowry acid? And I will post these notes. In fact, I can even probably make a printout of them, because I made a printout of my notes from block 3 for me, so I remember what I did. What is a Bronsted-Lowry acid? Proton, yes, a proton donor. Okay, now what is a proton? That is a hydrogen ion. Does it make sense as to why H plus is called a proton? Because if you take a hydrogen atom and you remove its electron, all you've got left is a proton. Yes, okay. What is a Bronsted-Lowry base? A proton acceptor, yes. You cannot have one of them without the other. Imagine that you were trying to donate a proton, but no one would take it. Yes? But you're not going to have any luck, and if nobody wants to give you a proton, you cannot accept one. You cannot have a Bronsted-Lowry acid without a Bronsted-Lowry base. They don't work. So let's take a look at what happens when we put a Bronsted-Lowry acid in water. I'm going to use HF because it's one of the shortest acids. A lot of the acids have like more long, complicated formulas. HF is nice and short. If HF is the acid, what must water be acting as here? It must be acting as the base. And what that means is that our hydrogen is going to be transferred from the HF to the water. So what is left after HF gives away an H plus? F. And we didn't just give away an H, we gave away an H plus. So what charge is the F going to be? F minus, because we took away a positive as well. Okay, that's aqueous. And if water has accepted that proton, what is the new formula of the new compound going to be, or species? H3O, and it didn't just gain an H, it also gained a plus. Yes, so it went from being neutral to being +1. Do you know the name of this species here, H3O+? That is hydronium. And this reaction here is what happens in reality. We'll have a quiz. We're having a quiz next Tuesday on the Bronsted-Lowry stuff. I know. Now, we could write this. Oh, actually, before we do that, in the reverse reaction, who is acting as the Bronsted-Lowry acid in the reverse reaction? So now you're looking at the products and saying who's acting as the acid, who's acting as the base. Tell your partner. And if there's no one around you, just tell the sky. What do you guys think? F is the? I heard both. Which one? It has to be the base because it doesn't have a hydrogen to donate, yes? And H3O plus has to be the acid because if you think about it, when we go backwards, H3O plus gives a hydrogen to fluoride and it becomes HF. And then H3O plus loses its proton and becomes H2O. So that's a reverse reaction there. This process, what's happening in reality, is called ionization. And that is a little bit different than how we've been writing acid, what acid does in water up till this point. Up till this point, we've been doing dissociation, yes? Where we've taken our HF and dissociated it into H plus and F minus. This is not what happens in reality, okay? This is what we call the shorthand version. Do you guys know what shorthand is? Any idea? No, okay. Shorthand, back in the olden days before we had like computers and voice to text and, you know, anything like that. So this would be like the 30s, 40s, 50s, 60s, okay? People who were doing business or, you know, lawyers or whoever, they would say things and their secretary would transcribe them. They would take what the person was saying and they would write it down exactly. Now, in order to do that, if you're writing, you need to be able to go very, very fast, yes? So there was a series of these little symbols and squiggles, and it was almost like an entire other language where these little symbols and squiggles represented syllables or entire words or phrases, and secretaries would go take a whole course in how to write shorthand so that they could transcribe what the person was saying. And so When we say the shorthand version, we mean it's like a shortened version that's not actual like reality. Yes? So ionization is what really happens. Dissociation is the shorthand version. And even though it is the shorthand version and it isn't reality, we still often use it because it is faster. Yes? It really does get to the point for most of what you need. And in fact, if we look at our data booklet, you can see on here, they haven't included water in these ones. Yes, they've just shown the dissociation. Yes? When a Bronsted-Lowry acid donates its proton, whoa, that did not look like acid. It turns into its conjugate base. Okay, so HF donated a proton. And turned into, what did it turn into? F minus, yes. Okay, so it turned into F minus. And F minus is called the conjugate base of HF. So when you hear that term conjugate, it means that the two are related, okay? The two species together are called a conjugate acid-base pair. So if you were asked to define a conjugate acid-base pair, this is the definition. A pair of chemical species that differ by what is the difference between F minus and HF? The H plus, so they differ by a single proton. So for example, HF and F minus are a conjugate acid-base pair. The two of them together make the conjugate acid-base pair. F minus is the conjugate base of HF. And HF is the conjugate acid of F minus. So at this point, I think it would actually be good to go to 4.1 up. So if we open up there, Bronsted-Lowry theory, putting it all together. Sadly, I don't think I numbered the pages in here. If you're interested in numbering them, you can just start numbering them at 42 and carry on from there. They were supposed to have been numbered, but I guess I didn't manage that. Oh, you don't have this one? So, as we said, if a chemical is acting as an acid, it loses a proton. So when a Bronsted acid, sometimes we leave off the Lowry and just call it a Bronsted acid, if it turns into its conjugate base, off has to come a hydrogen. Yes? So who is the conjugate base of HCl? Just like that? Minus. So you have to take off an H and you have to make it one more negative than it was before. How about HSO4 minus? SO4 2 minus and HPO4 2 minus becomes a, ooh, why did I leave the H? PO4 3 minus. Excellent. We can do the same thing for Bronsted bases. If they gain a proton, so when a Bronsted base turns into its conjugate acid, a proton is going to come in. And so, for example, CO3 2 minus would turn into HCO3 minus. CH3COO minus would turn into CH3COOH. Yes, this is one where if you put it on the beginning, it wouldn't technically be wrong, but it is better to put it on the end because this hydrogen here is the detachable proton. Yes, the ones that are attached to the carbon, the CH3, those ones don't come off. Okay. And if you, this next little bit is important if you're in biology or if you're planning on going further with chemistry in university. The detachable proton goes on what's called the carboxylate group. And that is the COO minus. Okay, and if you're interested, it actually looks like this: C double bond O, and then there's a negative charge. And then if you have it with this, we add on the H, it's C double bond O, bond H. Yes? So that's carboxylate. And that is carboxylate acid. And you can have anything attached to those, and those are your the important groups that happen at the end. But if you're not doing bio, and if you're not carrying on with chemistry after high school, then you don't need to worry about that. The rest of them are fairly straightforward. We have HPO4 2-. What is its conjugate acid? H2PO4, and its charge, sorry, minus. And then HCO3, H2CO3 minus. No minus. Why did I put a minus? Because it's been a long day and I've taught this lesson twice already and I'm going a little bit kooky. Okay. In the above examples, there are two substances that are acting either as an acid or a base. Can you find one of those substances or two of those substances? Can you see something that is labeled as a base and also labeled as an acid? Hydrogen what? Not just hydrogen, one of these things. The bottom two, yes. So we've got HCO3, and we also have HCO3 over here. So HCO3 minus is able to be both a base and an acid. Is there another one? We might have to look a little further up. HPO4 2-, yes. HPO4 2- is both a base and an acid. So we can write those down here. HPO4 2- and HCO3-. They can act as acid or as a base. In other words, they can either donate or accept a proton. Do you remember the name of chemicals that can act as either an acid or a base? You guys didn't like my picture of the frog enough to remember it? Amphi, yes, like amphibian. And they can both donate or accept a proton. So it's amphiprotic, yes. Amphi meaning both. Protic referring to being able to accept or donate a proton. It is important that you be able to spell this word. I know that seems trivial, but practice it because it's a little bit, weird, the spelling and all of that. It does help if you are familiar with the term amphibian. If you're not, then that's not going to help you. But amphibians can live both on land and on water because amphi comes from the Greek meaning on both sides. You guys heard the word ambidextrous? What does it mean if you are ambidextrous? You can use both hands. Yes, and ambi and amphi are from the same root. Okay? So another definition of amphiprotic, you'll notice I'm having you write it again just to remind you how to spell it, is a substance that can act both as a what donor? Proton donor. And what's a proton? H+. And as a proton acceptor. Okay. So how do we recognize these substances which are amphiprotic, which can act as both acids and as bases? Well, the first thing that an amphiprotic substance has to have is it has to have a hydrogen. How could you possibly act as a proton donor if you don't have a proton? Can you donate a hydrogen if you don't have a hydrogen? No. So you have to have a hydrogen to be amphiprotic. The second thing, and this is true most of the time, in fact, like 99.999% of the time, you also need to have a negative charge, because if you're going to be acting as a base, you need to be able to accept that positive ion. So it really helps if you have a negative charge. However, there is an exception to this negative charge rule, and that exception is water. It is amphiprotic even though it does not have a negative charge. But you'll find that all the rest of them that have a hydrogen and are negative are all amphiprotic, or at least almost all. Okay. We are going to take a little walk over here to the next page and familiarize ourselves, if we are not already familiar, with our table of acids and bases on page 6 of your data booklet. You have another copy of it, your purple copy, which you can use. I don't know why I gave you I do know why I gave you an entire another copy. It's because I added an extra base. You can see down at the bottom, there's 3 strong bases instead of 2 strong bases this one. You can see there's only 2 strong bases. The purple one, you have 3 strong bases. I don't know why. Anyway. So if you are able to print this out in color at home, it wouldn't be the worst thing in the world to do, because it is all color coded. All the acids, for example, are in red. Okay, so all our acids are in red. Why did I choose red for the acids? What does litmus paper do in acid? It turns red. What color does litmus paper turn in bases? Blue, and then hence I have colored the bases blue. And in addition, you can see that the strong acids, which are up here, they're in a darker red, yes? Our strong bases, which are at the opposite end of the table, way down at the bottom, they are in dark blue, and the weak bases are in a lighter blue, okay? So, squish this down, make that bigger, there we go. I really wish there was like a taller version of the projector, it would be better, but anyway. So just so you can see the whole thing at once, we have our strong acids. Down here we have our weak acids. And then down below that, you'll notice that there is a yellow section. Yellow isn't red or blue. That means they are neither acids nor bases. It means that we have our strong acids, we have our weak acids, which get weaker and weaker and weaker and weaker and weaker all the way to the bottom, where we have our weakest weak acids down at the bottom. And then finally, down at the very bottom, we have OH minus, which is too weak to act as an acid. Does it make sense that hydroxide is not an acid? Yeah? Space? Yeah? Okay. So OH minus is unable to give up a proton and become O2 negative. Okay? And you'll notice that that is a one-way arrow. Yes? And NH2, also has a one-way arrow going to ammonia. And I'm going to take a moment to draw your attention to ammonia, because people know, or at least you will get to know, that ammonia is a base, if you don't already. You will sometimes be asked, is ammonia a strong acid, a strong base, a weak acid, a weak base? And people get confused by ammonia because it is here. And they see that it is in this sort of gray zone, yes? This gray zone at the bottom is the home of the strong bases. However, the strong bases are not here. Those are the conjugate acids of the strong bases. And they are too weak to act as acids. So ammonia is not a weak acid, even though it is on the acid side of the table. Okay? Who is the strong base? Ammonia is not the strong base. NH2 minus is the strong base. These are our strong bases. So ammonia is not a weak acid. It is not a strong base. It's on the wrong side of the table. What is ammonia? Can you find ammonia somewhere else on the table? Take a look on your table, see if you can find ammonia somewhere else. Ooh, that's what I need to do here. There. Can you find ammonia somewhere else? Yes, it is over on the right-hand side of the table, which puts it in the white area of the table, which means that it's in the weak category, and it's on the right-hand side, and the right-hand side are all bases. Yes? So on the right-hand side, we have ammonia. It's in the weak area, so it is a weak base. Now, up at the top of the table, we have our 6 strong acids, and you'll notice that just like the strong bases, the arrows go only one way. So even though ClO4 minus is the conjugate base of HClO4, is it actually able to act as a base? Is it able to accept a proton? Is there an arrow going in the direction where it would be accepting a proton? No. Look at that arrow. I don't think I can make it any heavier. It's that way only. So HClO4 will give away its proton, and ClO4 minus will never take it back. Okay? So the conjugate bases of strong acids are actually too weak to act as bases. So if I was HCl, okay, I'm HCl. Simon, we need to wait for you. I'm HCl. I'm a strong acid. I side. I'm Cl minus. I'm Cl minus. Oh, no. Now, the other side of that is, I'm actually not running away from it. I am too weak to take that hydrogen back. Yes, I cannot take that. Cl minus is too weak to take the hydrogen away from anybody else. Wait now. Okay. They are too weak to take the hydrogen away from anything else. Okay, so there's our table. What have I missed? Ka. Okay, we won't talk about that very much today because that's going to be the next section, is the math part of it. But Ka is the KEQ for an acid. Yes? And if you have an acid, HA, in equilibrium with H plus and A minus, all of these things are aqueous. So it's not like in the solubility where we had a solid. The acid, and if this was my acid if the cap is the proton, okay? When I dissolve an acid into water, it actually mostly is undissociated and these things float around, you know, attached. A very small percentage of them will float around detached as long as it's a weak acid, okay? So our Ka is going to be concentration of H plus times the concentration of A minus over HA. So you'll notice that for our strong acids, what does it say about all of their Kas? They're all very large. And if Ka is very large, that means that you have 100% products, okay? You don't have any HA left, okay? So there's nothing intact. It's 100% dissociated, okay? You'll also notice as we get down into the weak acids, there are actual values for the Ka. Yeah, but we start with higher values and we move down into, we go -1, -2, it gets smaller and smaller and smaller and smaller as we work down the table. What does that mean about the percent dissociation for the stronger weak acids? Do we have a higher percent dissociated, or do we have a lower percent dissociated? We have a larger Ka, which means we have a larger concentration of the ions, yes, and a smaller concentration of the molecule. So when we have our larger Ka values, this means our stronger weak acids have a larger Ka, and they a greater percent, a larger percent of HA is dissociated into H plus and A minus. As we go down the table, the value of Ka is getting smaller and smaller and smaller and smaller and smaller, which means that we have less and less and less product, which is the dissociated ions, and more of the reactant, which is the intact molecule. So down in our weaker weak acids, and I'm sorry for this terminology, I know it sounds really stupid. We have our stronger weak acids and our weaker weak acids. We have our stronger weak bases and our weaker weak bases, but it's the only way really to refer to them. So our weaker weak bases, a smaller percent of the HA molecules are dissociated into H plus and A minus. And then eventually you get down into those substances which are too weak to act as acids, and then they don't make any H plus at all. Yes? Yeah. Up here? Oh, just here. Yeah? That, there, yes. I think it's going to be nap time when I go home. Okay. Let's go back to these notes, okay? Before we carry on. How does a Bronsted-Lowry base make OH minus? Because if we go to our data booklet and we're like, here's a Bronsted-Lowry base, and I see no OH anywhere. Okay, so this table is obviously not going to tell you how that happens. So how does a Bronsted-Lowry base make OH minus? Well, let's do an example to find out. Do you guys remember anything about NH3, ammonia? What kind of a compound is ammonia? Is it an acid or is it a base? It's a base. Is it a strong base or is it a weak base? Weak. It is a weak Bronsted-Lowry base. And if we react it with water, if it is the Bronsted-Lowry base, what is water going to act as? it's going to act as the acid. So the hydrogen is going to move from the water to the ammonia. What will ammonia turn into? Yeah, NH4 plus. And what is water left as? OH minus. Oh, look. How does a Bronsted-Lowry acid make OH minus? It takes a hydrogen away from water, leaving hydroxide behind. So you don't need to have an OH in your formula to actually make OH. You just need some water kicking around. Is there anything else I wanted to say there? I'm sure there was. What was it? Oh, yeah. Who are the acid and base in the reverse reaction? Who is giving the proton to whom? NH4 is giving the proton to hydroxide in the reverse reaction. So that would make NH4 plus the acid in the reverse reaction, and it would make OH minus the You'll notice that each side of the equation has both an acid and a base. In an acid-base equilibrium, excuse me, each side of the equilibrium needs to have both an acid and a base. Who are the conjugate acid-base pairs? Who is paired with whom? You remember what an conjugate acid-base pair is? It is a pair of chemical species that what? Yes, yes. That differ by, it's a pair of chemical species that differ by what? H plus. So who is a conjugate acid-base pair? Those differ by more than an H plus. Okay, NH3 and H2O do not differ by a single proton, so they are not a conjugate acid-base pair. NH3 and NH4, they are the conjugate acid and base of each other, which makes them a conjugate acid-base pair. So this is a conjugate acid base pair, those two. And then our other two also differ by a single proton, right? H2O and OH minus only differ by a single proton. That is our other conjugate acid base pair. So if we had to list them, we'd say we have NH3 and NH4, and we have H2O and OH minus. And I'm just going to write down once again, they differ by only one H plus, just to remind us. Now, this is going to be a kind of a weird sounding question, but it actually kind of makes sense, so just bear with me. When you look at the two members of the conjugate acid-base pair, what can you say about them and their relationship to the reaction arrow? We got one acid-base pair here, and there's our reaction arrow. We have another conjugate acid-base pair here, and there's our reaction arrow. Yeah, the conjugate acid-base pair, one member is always, they're on opposite sides, okay? So the two members of a conjugate acid-base pair are always on opposite sides of the reaction arrow. And that has to make some kind of sense, yes? If I am an acid, how do I become my conjugate base? I have to react, yes? And in that process of reacting, I have turned into my conjugate base. So I have to be, in my two different forms, I have to be on opposite sides of the reaction arrow, yes? Okay, back to 4.1F. I don't know why it's gone to the beginning again, but that's okay. We will keep flipping until we get to where we are. We went through this, blah, 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 blah. Going. Ooh, just a few little notes. The larger the Ka, the stronger the weak acid. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. Okay, so you're either good at being one or the other. Remember, I was really good at giving away my proton, but I was really bad at taking it back. Okay, that's just a little bit of blah blah blah. So we're just going to skip past that. It's just saying all the stuff that I said when we were talking about the table. So we are going to look at example 1. Is HSO4 minus amphiprotic? What two things did we say a substance needs to be amphiprotic? They need a negative charge. Yep, they need a negative charge and a hydrogen. So far, HSO4 is looking pretty good. Yes, HSO4 minus. It's got that hydrogen and it's got that charge. So what we're going to do is we are going to now go to our data booklet. Okay. I'm going to erase all this nonsense from my last block. And we are going to look for HSO4. Oh, look, there it is. About 5, yeah, 1, 2, 3, 4, 5 down from the gray zone up there. Yes? So this iteration of HSO4 minus is on the left side of the table. That means that according to the table, it is what? Acid or base? Acid. And it does have an arrow that goes that way. Yes? So we can say, is it an acid? Yes, it is. How about HSO4 minus as a base? Can you find HSO4 minus on the base side? On the right-hand side? If you can't see up here, take a look on your own table. Let me know if you found it. Ah, here we go. Yeah, it's in that gray zone, yes? So technically it's on the base side, but what do you notice? That arrow goes only one way. So even though it's on the base side, it is too weak to act as a base. Okay? So is HSO4 minus amphiprotic? No. Okay? It is the only exception to that rule that I know of. Okay, it's the only common exception, certainly. If we look for any other species that has a hydrogen and a negative charge, let's just pick our first one we come across. Here I've got HC2O4 minus. Is that, what side of the table is it on? Is it acid or base side? It's on the base side. Is it able to act as a base? Yes, it is. It can go this way. So base, yes. Can you find HC2O4 minus on the acid side? Yep, there it is. Okay. There it is on the acid side. Is it able to act as an acid? Yes. So you'll actually see that if we could go through all the other examples on the table, anytime you see an H and a minus, other than H2SO4, they will all be amphiprotic. You have to memorize HSO4, not if you're willing to look it up and go, oh, it's in that section that's too weak to be a base. Okay? All righty. Oh, back to the beginning again, hey? Goodness. Okay. So this just talks about what we just talked about. More amphiprotic stuff. Here I have HCO3 minus. It has an H and it has a minus. Therefore, what do we know about HCO3 minus? Has an H, has a negative. It is amphiprotic. So how do I know what it is going to do when it gets together with phosphate? It's going to act as either an acid or it's going to act as a base. but which one will it do? Acid, why? It has a hydrogen, and more importantly, PO4 doesn't have a hydrogen. So PO4 has no H+, therefore it has to be the base, and if it's the base, then HCO3- must be the acid, okay? So here, HCO3- acts as an acid because PO4 3- is a base capable of accepting a proton. So who would the products of this reaction be? CO3 2- plus H PO4 2-. We just moved an H+ from the HCO3 to the PO4. Who are our acid-base pairs? Oh, first of all, who is the acid and the base in the products? CO3 2- is the base because it ain't got no hydrogen, yes. And HPO4 is the acid. If we wanted to identify our acid-base pairs, who does HCO3- go with? Who is its conjugate pair? CO3 2-. That is a conjugate acid-base pair. Who is our other conjugate acid-base pair? PO4 3- and HPO4. That is our other conjugate acid-base pair. Okay. Predicting which side of an acid-base reaction is favored. Oh my gosh, favored. What does it mean if a side is favored? It means that those concentrations will be higher at equilibrium. If a side is favored, its concentrations will be higher at equilibrium. So we're going to predict whether we favor the reactants or we favor the products in an acid-base equilibrium. And what we're going to be doing is mixing a weak acid with a weak base. We're not going to worry about water at this point. We're actually going to throw a different weak base in there. So in this case, we have HCN and F-. Who is the acid and who is the base? F is the base, HCN is the acid. So who are our products going to be? Hydrogen is going to now transfer over. CN- because the H is gone, H+ is gone, so CN- and HF. So we're going to have a situation where either we have more reactants or we have more products, yes? In order to decide Actually, first of all, let's see. Can you recognize your conjugate acid-base pairs? Who is a conjugate acid-base pair? HCN and CN minus, that is a conjugate acid-base pair. And our other conjugate acid-base pair, F minus and HF. So who are our two acids in this equilibrium? Who are the two acids? HCN and HF. Who are the two bases? F and CN. So if you remember, back when I was a really strong acid, yes, I gave away my proton and never took it back because I was a really weak base. I was like, oh, I cannot take the hydrogen. Okay? Whoever is the stronger acid will be better at giving away its protons. Yes? So if we go and we look on our acid-base table and we look for HCN and we look for HF, here is HF. Yes. Here is, I think HCN is like down near the bottom. Here's HCN. Who is the stronger weak acid, HF or HCN? HF is the stronger weak acid. You can actually see HF has a Ka value of 10 to the negative 4, whereas HCN, the Ka is 10 to the negative 10. So it's much less good at giving away its protons. Yes? So HF is the stronger weak acid. Let's go back here. Please don't go back to the beginning. Yes. Okay. So this is the weaker weak acid. And this is the stronger weak acid. So HF is better at giving away its protons. So how is it going to spend most of its time? Is it going to spend most of its time as HF, or is it going to spend most of its time as F minus? It's going to spend most of its time as F minus, which means that my reactants are favored. Sometimes I like to think about it this way. The acid pushes the reaction away from itself. The stronger it is at pushing the reaction, it's going to push the reaction away, and so whichever side is opposite it will be favored. We will go over this again next day because I know we're cramming it in like the last minute before the bell. So after your test, we will be carrying on with more of this. I will be here during Flex tomorrow, so if you're interested in dropping by for a little help, I can certainly do that. Hello. Oh, I needed to pick an ion that would precipitate one of these. So I picked either chloride or bromide or iodide or sulfide. Now, Why sodium? Because if I take sodium chloride, sodium pairs with everything and dissolves with everything. So I will have free floating chloride ions. Why Cl? Because I want something that is going to precipitate one of these three, but no more. So if I pick Cl, it will precipitate the lead, but it will not precipitate calcium and beryllium because they belong in the all others. Okay, I could not choose sulfate because it would precipitate both calcium and the lead. I needed to separate them out one at a time. You know that lab we just did? Where you took the ions out one at a time? If I add sulfate and I get a precipitate, I have no idea whether that's calcium sulfate or whether it's lead sulfate or both. But if I add chloride and I get a precipitate, I know it had to have been lead.
So you can only choose one and not two.
You have to choose one that precipitates one, but not two or three.
Yeah. Or just less than one.
You have to do one at a time.
Okay.
So, for example, you couldn't choose sodium, or sorry, you couldn't choose nitrate because nitrate wouldn't precipitate with any of them. Right? So that's not helpful. You couldn't choose phosphate because phosphate would precipitate with everything. So you'd get a precipitate with phosphate, but it could be the calcium, and you're trying to decide, do I have calcium? Do I have beryllium? Do I have lead? And if I add phosphate, I get a precipitate. It could be any of them, and I don't know which one. But if I add chloride,
So you just pick it one at a time.
One at a time. Yeah, yeah. Yes. When you square them, you do it when it's got a coefficient of 2. When you're working with a KS2 value and you've got a 2 coefficient, you will square it. Yes, also squaring, because you would have, right? Sure. Yeah, because you got to go now. Okay, don't miss your bus. See you tomorrow. How's it going, Hayden? It's all right? Yeah. Which one? Sorry? Yeah? You're struggling with that?
Yeah, I think that was it's just very hard for me to
There are a lot of steps. Yeah. And you got cheated last year because we didn't get a chance to do that with the quarter system. So I apologize for that. Yeah. COVID. All right, take care.